Welcome back to Practical PyTorch. On a GPU, calling many tiny ops can be slow. That is true even when the math is the same. Let's find the hidden cost and then make it disappear. 100 tiny GPU calls can lose to one big call. That holds even when the arithmetic is identical. The reason is a fixed toll. You pay it at every single call. Every op you run is a kernel launch. Each launch has a fixed cost. You pay it no matter how tiny the work. Run 1,000 tiny ops and you pay that toll 1,000 times. Same math, very different speed. We will measure the toll first, then we make it disappear. This video has 3 parts. First, the fixed toll. Every op is a launch and each launch costs the same. Second, the anti-pattern measured. 1,000 tiny ops against one batched op on a real GPU. Third, batch it or fuse it. The fix is simple. Do more work per launch. Part 1. The fixed toll. When you call an op, PyTorch launches a kernel on the GPU. That launch has a fixed host-side cost. It covers dispatch and setup. It is the same kind of per op cost the dispatch lesson opened up. You pay it on every call, no matter how tiny the work. 1,000,000 elements or just 64, the toll is the same. This micro benchmark isolates one slice, the launching queue cost. Here it is about 8.44 microseconds per launch. That differs from the dispatch lesson's synchronized per op figure. It measures a different slice, so the two numbers are not equal. On a big tensor, this toll is a rounding error. On a tiny tensor, the launch is almost the whole bill. The GPU sits idle between calls. Same fixed toll per launch every time. On tiny work, it dominates. Picture one GPU lane. Everything runs on the single timeline from left to right. Each thin bar is one op. It does its tiny bit of compute. There are many of them in a row. Before each bar sits a wide dashed gap. That gap is the launch. The gaps are far wider than the bars. This annotation marks the fixed per launch toll. So the launches dominate the timeline, not the arithmetic. You saw gaps in the profiler lesson too, but there the GPU waited on the data loader. Here, each gap is the launch itself. Part 2. The anti-pattern measured. First, import torch. Build 1,000 small tensors. Each one has shape 64 and lives on the GPU. Stack them into one tensor. Its shape is 1,000 by 64. The loop function applies ReLU in a Python loop. That is 1,000 separate launches. The batch function applies the same ReLU once to the stacked tensor. That is one launch. Both use the honest method from the timing lesson. Warm up first, then take the median of many repeats. The arithmetic is identical. A ReLU runs on every number either way. Only the launch count differs. Look at the numbers measured on a real GPU. The Python loop takes 8.44 milliseconds. That is 1,000 tiny ReLUs, 1,000 launches. One batched ReLU takes 0.019 milliseconds. That is one launch. Divide the loop by 1,000. Each launch costs 8.44 microseconds. That is the fixed toll. The batched op is 441 times faster for identical arithmetic. Now be honest about the framing. 441 times is the extreme case. It is a micro benchmark of truly tiny ops, built to make the fixed cost visible. It does not mean every loop is that slow. Part 3. Batch it or fuse it. The gap is huge. A linear axis cannot show both bars at once, So this chart uses a log scale. The tall bar is the 1000-op loop at 8.44 milliseconds. The short bar is the one batched op at 0.019 milliseconds. The note marks 8.44 microseconds per launch. On a linear axis, the batched bar would simply vanish. The log scale makes the 441 times gap visible. The timeline now shows the fix. The 1,000 thin bars collapse into one wide bar. The whole workload runs at once. The note says it plainly. One launch now instead of 1,000. Only a single launch gap sits before the bar. The overhead is paid once. Batching does more work per launch, so the fixed toll is paid one time, not 1,000 times. Now line the two runs up. The top row is the loop, a short bit of compute, then a long stretch of overhead. The bottom row is the batched op, the same short compute with only a sliver of overhead. Look at the green compute segment. It is the same length in both rows. The arithmetic is identical either way. So the loop row's extra length is pure launch overhead. That is the only difference between them. The method is one line, do more work per launch. Batching repeats the same op over more data in one bigger launch. That is our worked example. Fusing combines different ops into one kernel. Torch Compile does fusion for you automatically. That is the next lesson. The classic version of this bug hides inside a training step. It is a Python loop over the items in a batch. It runs one small op per item. Looping over the samples looks perfectly reasonable, but it turns one GPU workload into a launch latency workload. Hundreds of tiny launches, where one batched op would do. If you are looping over samples in a batch, you pay the toll per sample. Vectorize across the batch instead. Every op is a kernel launch. Each launch has a fixed toll. Here it was about 8.44 microseconds. A loop of tiny ops pays that toll thousands of times. The launches fill the timeline, not the arithmetic. Measured, 1,000 tiny ops took 8.44 milliseconds. One batched op took 0.019 milliseconds. That is 441 times, for identical math. The fix is to do more work per launch. Batch it or fuse it. That is the problem the compile lesson exists to solve. Quick check before we go. 1,000 tiny ops or one batched op on the stacked tensor. The arithmetic is identical. Which is faster and what is the extra cost made of? Pause and predict. The batched op wins by about 441 times here. The extra cost is the fixed per launch overhead. It is about 8.44 microseconds, paid 1,000 times. That is roughly 8.44 milliseconds, which swamps the tiny arithmetic. Remember, 441 times is this micro-benchmark's extreme case. The full reasoning is in the course answers file. You now know the toll, and you know the fix, fewer, bigger launches. Next comes Torch Compile. It is the decorator that does this for you. It captures many launches into few. It also has rules about what it can and cannot see. That is the next lesson.